Hey, welcome back, everyone. We're going to take a look at what's inside of our Earth and how we know what is inside of our Earth. So, let's take a look at our Earth layer notes. So, if you think back to last class and last few classes, we're really looking at you went through the CER, you've read the section, you know that we have multiple layers to our Earth. So, I want you to take a second and just think about and make a quick list of how we know what the different layers are and kind of start thinking about what their composition is. Now, when you're done with that, let's go really talk about what the layers are. So we know that we have three basic layers. We have the core, we have the mantle, and we have the crust. But each of those are divided into smaller layers. For example, the core is the inner and the outer core. That's easy to see here. Then we've got the mantle, which has a couple layers in it, and that's that plastic kind of silly putty like. This is our hot magma coming up that erupts into lava once it hits the surface. But to get to the surface, it has to break through the crust, which also, guess what, is split into a couple different layers. So that's what we're really going to look at now. Or what are the layers and how are they broken up? For years, we didn't really know what was in there until we started studying earthquakes and getting that data. Now, we've known about earthquakes since humans have been around because this is a really old earthquake indicator, and it would tell them the direction from which the earthquake came from because the little ball in the mouth would fall out into the waiting mouth of the frog below. Sometimes these actually had sand in them or water too, so it would depends on what kind it is. But I believe this, if you look very closely, has a ball in the jaw of the dragon on top, waiting for the frog below to catch. Well, we don't really rely on that anymore. Still cool to see. If you ever go to the Science Museum, and when you hear the tones go off, that is actually an indicator of the earthquake. And the song and the tonality tells you where it's originating from and how intense it is. But even they need this equipment that I'm showing you right here, which is a seismograph. And a seismograph is planted really firmly into the bedrock so that it will shake. And then it has this revolving piece of paper that just kind of scribes, and the tip of the pen stays just really lightly on the paper. And basically, in most cases, that weight stays steady and everything below it can shake, or the pen can shake. And in this case, the pen is shaking as it goes back and forth with the earthquake. Now we have something called SL and P waves, and they travel through different media at different speeds. And some can travel farther than others, which is what we'll talk about in a moment. So earthquake happens, the waves radiate out in all directions, every direction, and has to travel through. And then we record them at different locations. And as the waves arrive at different location, that time lag actually allows us to figure out where the epicenter was and how deep it was into the earth. And as we look at that depth of the earth, what we're really seeing here is the focus. The epicenter is where the earthquake occurs. The focus is the point directly above it up on the surface. It's a little precursor to what we're going to learn coming up here. And when that earthquake occurs, surface waves go out in all directions from the focus point, the point above the epicenter. And down here at the epicenter, it also radiates out in all directions with their S and P waves. And P waves, they can travel through anything, but they do get a little bent when they go through this mantle boundary to the liquid core boundary. When it hits that liquid, it actually gets deflected a little bit, and it comes back out, and then it gets deflected back when it comes back through. And we know how we can measure these waves. We can reproduce them in a controlled environment so we can see how they go. So we know that these waves can make it a really long distance and all the way around to basically the other side of the world. But our S waves, they don't like liquid at all. They don't travel through it. In fact, it will get bounced back up. And so where the distance is coming back here, that really allowed us to find out how far down that mantle really starts. And that's how we define the edge of the mantle. It's a place where these S waves just couldn't penetrate and they would get reflected back up. And they also travel through and then come back to the surface. And again, we can measure these time legs to figure out and work backwards. But it's that ability to not travel through a liquid that allowed us to determine the mantle depth and where the core starts. And then these waves getting bent through it, that's what led us starting to really see kind of the layers of the core, the inner and the outer core. Because again, this inner core we're going to talk about is special, and we'll get to that in a minute. But really, we're talking about earthquakes. And those waves allowed us to see what is inside of our Earth. Because let's face it, we don't have a big magic X-ray machine. Oh, wait, we do. They're called seismographs, and they let us see what's going on the inside. But you can't just look through it. You can't dig a dig hole because it will collapse. Gravity wins. So on your notes, I have given you guys it's printed here. There's a PDF of it in the folder. But if you're in class, obviously, you would have gotten it handed out to you. And I want you to go through those notes and fill them in as we go through, because that's a really good review for the test. So our inner core, inner and outer core, we're just going to go through some basic, what is it? What's it made out of? How deep is it? How hot is it maybe even? So let's get started. So the center of the Earth is our inner core. This is the place under the heaviest compression. Gravity is pulling everything to the center. This is our densest, heaviest layer, and it's made of solid iron and nickel. And it makes sense because those really dense materials are pushed down farther and farther into the center of our Earth. And even though it's hot enough in the inner core that it should, in fact, be a liquid, that iron and that nickel should be melted, it is under so much heat and pressure that you need to actually realize it acts like a solid. So one of the things I want you to do on that little graphic next to your notes is I want you to highlight where is the inner core. What are we talking about on that picture? So I want you to actually draw on it where you're seeing the inner core. Okay? If you need to pause, go for it and fill in your notes, because obviously they're on the screen. You can do that. But let's take a look now at the outer core. If you've unpaused, here we go. So the outer core is liquid. It's just above the inner core, and it's 2,250 kilometers thick, where the inner core was 1,200 kilometers across. Because remember, that's a sphere, so we're going straight across right here. But this 2,250 kilometers thick, that's this part right here. It's that next layer out. It's that outer core. And this is still mostly iron, but it's easily magnetized. And that's important because this layer, this spinning mass of iron that can be easily magnetized, which is really important, that's what causes our magnetic field. That's that invisible force that comes out of our poles at the north and the south part of our world and funnels all the northern lights. So all that raw energy from the sun, that magnetic field is what shields us from it. And this should be reviewed from all the way back into last semester. So northern lights are cool, but they're created because of the magnetic field, which is created on our planet or generated on our planet because that outer core is spinning quite quickly around the inner core and it magnetizes. Again, anytime you need to pause it to fill in those notes, you go for it. And if you haven't done it already, make sure you're marking now where the outer core is on your diagram. So the core is so hot that it radiates heat all the way up through the upper layers. And we get convection currents going because of it. And those convection currents, they get this hot, hot stuff down here. And remember, hot liquids, hot fluids rise. In this case, it's a liquid. It's a sticky liquid called magma, but it's a liquid. And as it rises, it can actually push the crust in opposite directions. So we have this thing called the Mid-Atlantic Ridge, which we'll talk about in great depth coming up. But it's because of these convection currents that the ridge is splitting apart and actually making us get just a little bit farther from Europe. And that's also a little precursor to tectonic plate movements. So the core is hot and we have convection currents going that radiates up. which causes plate movement. And again, just a little precursor of what to know. You need to understand that this is where the heat's coming from to get the rest of this unit coming into play. And we talked about these magnetic field lines here. And it's well known that the axis of the magnetic field is tipped and it wobbles. And sometimes it's in Russia, and sometimes it's towards the North Pole, and sometimes it's closer to Canada. So because it doesn't wanders, it literally does wander. We can measure this crazy wandering path of where the field goes. True north and magnetic north are not the same. So the North Pole is true north. It's 0, and you take our longitude and our latitude off of that. But magnetic north, if you ever fly an airplane, we have to compensate for it. So they adjust where is magnetic north compared to true north. And there's settings on an airplane that allow them to do that so that they use the magnetic North Pole to find where is north, which allows them to safely traverse the skies and get us from place to place. And that's a great thing. So those magnetic fields are produced by the motion, basically electrical charge. Those ion particles spinning generate an electrical field, which generates some magnetism. And it's kind of like, for example, a magnetic field on a bar magnet results from the motion of negative charges in the electrons. In this case, our charge is occurring because the iron is spinning around the inner core. So we know the origin of the Earth's magnetic field is not completely understood, but we understand how, we can put a bar magnet on here and we can see the pole lines. We can see this is if we could look at this from the Earth out, and these would be our field lines. They come in one side and they go out the other. And with that, we have this protective sheeting. And there is a mechanism that generates all this called the dynamo effect. Basically, it's that spinning outer core around the iron and nickel inner core. And we get our magnetic field lines. And with that, we get beautiful northern lights. And if you ever get a chance to go farther north, we can see them here sometimes, but often they're just white, sometimes a tinge of green. And last summer, fall, we actually could see them, but you really had to take your camera out to get the other colors to see it. It was too hard to see with the unaided eye. And while we're talking about the northern lights for just a minute, pause that because you don't need the sound. And we're going to make that jump ahead just a teeny tiny bit. Oh, didn't mean to do that. Hopefully it's not going to pop up for you. And we can see these. Interesting. Will not let me play 2 at one time. So we'll just watch one. But you can go in and look at the other one. But this is what happens when the sun's energy gets funneled in around our magnetic field and interacts with our air molecules. So in the spectrum, when you heat a gas, you get different colors. So all those colors tells us we've got nitrogen being excited or oxygen, and we get these beautiful colors as those energy levels are pushed from one level to the next. And that's our northern lights. So again, if you ever get a chance to see them in real life, take it because it's amazing to see. All right. This is actually what you can see from the International Space Station. And this is Antarctica, if I remember correctly. If my orientation is right. And they're not just across the sky, they go up and down too. And so there's depth to them. And this one is, again, we're not going to watch the whole thing. But this is from the International Space Station, and they have the best view of the northern lights. And they go around so quickly that it's dark, and then all of a sudden, yep, there they are again. And so this is our northern lights from space, and they are breathtaking. If you ever get a chance, and an astronaut is something you want to be, and you get to go out into space and see this, it would be an amazing sight to see it from the top down. But again, this is the sun's energy being funneled through our magnetic field lines, and all that is because our outer core spins around our inner core, creating a dynamo effect. So now let's go to the mantle. And as we look at the mantle, this is the layer directly above the outer core. And again, you should be indicating this on that little sheet and highlighting which part we're talking about. And the mantle is located, again, just above the outer core, but below the crust. It's the largest layer. I mean, if you think about it, as a sphere gets bigger and bigger, it's just going to have more area. And it's also 2,900 kilometers thick. So again, this is just a big layer. It's big because it's got a big circumference, but it also has a very thick depth to it either. And these are basically plastic, movable. Think of kind of like silly putty consistency. It's composed of minerals rich in elements such as iron, magnesium, silicon, and oxygen. And these are the source of our mafic minerals. So if you go back to rocks, remember our mafic is our handy dandy rocks that make up what? Think about it for a second. Are those our continental rocks or are those our basaltic rocks? So this is hot, soft rocks, rich in magnesium and iron. Its density increases with depths due to increasing pressure, and that would make sense. The farther down towards the center, you're going to have more pressure, so therefore the density increases because it's got more squeezing it. And if we look here, just as kind of a cross section, here's our inner core, here's our outer core. That's the one that creates our dynamo effect and creates our magnetic field. And this is that squishy, plasticky mantle layer. And we divide it actually into the upper mantle, right below the crust, and the lower mantle, right above the outer core. So that's the next thing we're going to take a look at. What are those things called? Well, these are the lithosphere and the asthenosphere. And the lithosphere is that crunchy layer of the earth. It actually does technically include part of the crust and the uppermost part of the mantle. And we kind of think of it this way. It's a density difference. It's the crunchier part. It's cooled a little bit part. It's that long, long, long cooling time to get those big crystals in granite. Where the asthenosphere is soft, this is that plasticky part of the mantle. And it's really the layer portion of the mantle located right below the sphere, but above the outer core. And it kind of floats here, like think of Jello with another layer of Jello on top of it. And they separate a little bit by density. So we've got the lithosphere, the crunchy, close to the crust, and the asthenosphere, the soft, bendy, like plastic part layer, just the upper portion of the mantle. And it's located right below the lithosphere. So lithosphere, asthenosphere. And again, these would be things that on a test, I'm going to be more concerned with crust, mantle, inner core, outer core. But I am going to ask you questions on the lithosphere and the asthenosphere. So just be warned. So let's kind of go through it a little more. The lithosphere comes from Greek for lithos, which means stone. So it's that rigid outermost layer of the crust and the upper part of the mantle. Okay. The lithosphere is the plate in the theory of plate tectonics. This is the part that moves. This is the part that can subducted. You know, we've got the really dense ocean floor can get pushed underneath continental. We'll talk about that in a minute. The lithosphere is that plate, and again, plate tectonics. It's about 100 kilometers thick. It's hard. It's not soft and squishy. And it floats on top of that squishier part of the mantle. And it runs anywhere, depending, from 100 kilometers thick, really to as shallow as 20 to 70 kilometers thick. At the ocean, you go down to 8 kilometers thick. It's really quite thin. Now think about it. At the bottom of the ocean, you've got all the pressure of the water that kind of cools it, but it also is just that much closer down compared to the continent that rises up out of the water, can have a much greater depth before you're going to hit that mantle layer. So the asthenosphere is Greek from asthenos, devoid of force. Okay, it is part of the mantle that flows, and it's called that plastic-like behavior. It's the part that spreads. And as the asthenosphere is part of the mantle convection, which plays that important role in moving the lithosphere. So this is the part that has the convection currents going up and down, and sometimes they go up and they spread. And when they do this, they drag on the bottom of the crusty part and they pull it apart. And as it pulls apart here, it's got to come together somewhere else. And sometimes we can have subduction, where we have continental and ocean plates meet. One can get subducted and remelted and gets recycled all over again. The rock cycle, it goes back to being magma. So soft fluid can be 3,000 kilometers thick in places. Again, it kind of depends on where the heat is going. The last one we're going to talk about, which is, remember, part of the lithosphere is also included in the mantle, is also part of the crust. And we're talking now the outermost layer of the Earth. Again, mark it on your diagram. Point to the part we're talking about so you have that in your notes. And again, this thickness varies drastically. Under a mountain, it can be as thick as 60 kilometers and as less as 5 kilometers to 8 under the ocean floor. This has the varying thickness of what we're really looking at. It is the least dense layer. Think about it. If you have water and oil floats on top of water because it's less dense. And we think, well, but you're talking basalt and you're talking granite. These are really dense rocks. Yes, they are. Feldspar and all of that good stuff. It is a nice hard rock that we can use for counters. But compared to the iron and nickel down below it, this stuff is like ice cubes floating in water. In fact, these hard rocks that we talk about are literally floating on top of these magma materials underneath. And they are just not as dense, so that's why they rise to the surface. So it's made up mostly of silicon and oxygen, just so you know. You don't think of oxygen being trapped up in rocks, but they do, like rust. Oxygen bonds with iron. And so we've trapped a lot of those elements in our layers. So the crust is rich in elements, again, oxygen, silicon, and lesser amounts that we think of we must have a lot of, but lesser amounts of aluminum, iron, magnesium, calcium, potassium, and sodium. So as it flows, interestingly enough, the ocean's crust is very dense, and this is our basaltic rock. It's a very dense rock compared to the granite, which is a much less dense rock. Granite is less dense than basalt, and that's going to be an important point coming up as we get through the theory of tectonics. So before we kind of transition from layers, I want you to think back and take a quick reminder as we look at this. Our density increases as we go down to the most dense layers in the inner core. Gravity pulls and pushes it all together with the least dense stuff on top of it. Now, we've already done the really least dense stuff, and that's our atmosphere. Because remember, our atmosphere, we've got our crust. Water flows on top and floats on top of that crust. And on top of that, we have our big atmosphere above it, because that is obviously the least dense layer that we have. And now we're focusing here. So looking at that, thinking about everything that we learned last week or a couple days ago, however you want to look at it, and looking at the CER we did and looking at the notes we've just talked about, I want you to turn, if you've got somebody else you're working with, and this would classes be where we turn and talk, but I really want you to stop and think for a minute and explain here, how do we know the Earth is divided into distinctive layers? And I want you to summarize it in a single sentence. So again, if you're in class, you're going to stop, turn and talk to your neighbors, and I really want you to come up with a good sentence that explains how we know the Earth is divided into distinctive layers. I'm going to pause this you can pause it for a big second. I'm going to pause for just a second as you get a chance to do that. And then when you're going to come back, we're going to take this and give you a hint of what's coming up. And that really is, we're going to take this understanding of the most dense material that sinks all the way to the bottom. And as we go up higher and higher, it becomes less dense and a little cooler, obviously, at the surface than it's going to be at the core. And then now we're going to start playing with that information. And this is where we get into the shake, rattling, and rolling. So give yourself a second here. Take a minute, come up with your sentence, make sure it's a good one, because remember, I'm going to read it, and I'll give you some feedback if I'm I want you to tweak it a little bit. So take a moment, pause it, come back. Okay. Hopefully you've unpaused, and here we're going to go. Again, remember we talked about a second ago that basalt is much more dense than granite. And so granite, by default, is what has kind of risen up higher than the ocean floor because it's less dense. It can ride up above it. And that is our mafic material. And within it, this is our granites. And these are what we're talking about. So really dense ocean floor and less dense continental. This is where the shake, rattling, and rolling comes into play because we can get those convection currents and we can start them moving. And we can get split over here where they're not really showing it too well because it's off this, but we'd have like a ridge where it splits apart. But where it comes together, that oceanic crust, because it's more dense, can get pushed underneath it. And we can also have like, this is called subduction, where that crust comes down and gets melted. If we had granite hitting granite, that's where we get mountain building. And the only, like the Himalayas, the only place it can go is up. But this is where we get a subduction zone. And where that comes down to melt, it creates hot spots. It wants to melt all that material and get it back up. And this is our ring of fire. And this is like in Washington State, in Oregon, and through Alaska, where we've got, and all the way down through Mexico, basically, it's the whole ring of the Pacific. This is where we get our subduction-formed volcanoes. And that's really important coming up, or what we'll talk about. But the other thing I want to give you a little hint to is the asthenosphere. If you get a really heavy weight on it, like we're talking, mountain ranges, or we're talking 5 miles of ice in a glacier, you can actually, if you have a heavy enough mass like a glacier or a mountain, you can actually depress the asthenosphere. And this is actually happening right now. Anywhere there's a mountain range or there's a massive glacier, it actually depresses down into the mantle. Think of it as like, in the 70s when they had the water beds and you'd sit on it, well, it displaced it and you'd have a little dent where your butt was. You're going to have rebound eventually if it goes away. And that's what's happening in Hudson Bay. Hudson Bay in Canada is where the last huge glacier started from. And it had so much mass because it was so many miles thick of just straight up ice. It actually deformed our asthenosphere and it created Hudson Bay. What's really interesting is because it doesn't have as much pressure on it, it's got water, but it doesn't have 5 miles of ice or a couple miles of ice. Hudson Bay is actually rebounding. The asthenosphere is actually bouncing back almost up to a foot a year. So eventually Hudson Bay might be just a really shallow lake. Not this big bay that we're used to today. So this, again, is our solid inner core, our liquid outer core, our plasticky mantle that has the asthenosphere and the lithosphere that's part of the crust. And these are the things that we're going to start moving around on the planet and talking about how all these things move. Our subduction, our mountain building. Again, the upper mantle, that plastic-like asthenosphere, our crunchy lithosphere that really goes all the way up to the crust. And I want you to answer one more question for me. Even if you just do it in your head. If we can dent the asthenosphere so it could be changed, again, where is it going to go when you take the weight off? In your head, you should be able to answer that question. But we're going to spend a lot of time talking about it. And if you've said it'll bounce back up, you're right. So this is what we have coming up. This is our plate movement. This is our convection currents. We've got our splitting. We've got our subduction. And all of that because we now know the mechanics of what the interior of our planet looks like. Helps us understand how those plate boundaries start working about. So we're going to get into mantle convection next, and then eventually get into plate tectonics and mountain building and the shake, rattling, rolling of our earth. And I hope you enjoyed this. Make sure you're taking a moment and going through and answering those questions before you hit submit. If you've got questions, as always, please email me. Have a good day.